Back in the 1930s or so, it was realized that the mass of a nucleus, if you were to calculate it based on how many protons, how many neutrons you have, is always ends up being greater than the mass that you actually measure. And this was because of what we call the mass defect. It's a manifestation of how uh, the forces holding the nucleus together, um, it has to come from somewhere, and it comes from the mass, and that comes from E equals mc squared. Okay, and so we have to be able to calculate what that mass defect is. And so there are two ways of going about calculating mass defect. One is if you're given the grams, and the other one is if you're given what's called atomic mass units. So we're going to do if we have the grams first. So the general procedure is you add up however many protons you have, the mass of all the protons, and you add up however many neutrons you have, the mass of the neutrons, and then you subtract it off the measured mass, the experimentally measured mass of the nucleus. Now, if you are given the atom, you also have to subtract off the electrons. We won't do that today. We're going to be assuming here that we have just the nucleus. And so we have our first problem here. The mass of a uranium-235 nucleus is 3.902995 times 10 to the minus 22nd grams. And we're given the mass of each individual proton and the mass of each individual neutrons. And we want to know what's the mass defect and what's the binding energy. So what we're going to do is we're going to go ahead and add up what we have here. Now, uranium is element number 92, so that means we have 92 protons. And we're going to multiply it times the mass of each individual proton. And we're also going to add in the neutrons. And if we subtract off 92 from 235, we got 143 neutrons. And we'll go ahead and multiply this as well and add them up. And if we do that and we put that in our calculator, we get 3.933958 times 10 to the minus 22nd grams. That's what we would expect. This is our expected value for the mass of the nucleus, but we go do an experiment and we find out that the actual mass of the nucleus is right over here. And so we say we have to subtract that off, 3.902995. And the reason why we go out 5 or 6 decimals is simply because the mass defect numbers are actually pretty small compared to the relative size of the atom. And we say that's times 10 to the minus 22 grams as well. We subtract off the 2, and we get a mass defect of 3.0963 times 10 to the minus 24th. That's my mass defect. It is the difference between what we calculated versus what we measured. Okay, now we need to get the binding energy, and we have to be very careful here because it is going to be E equals mc squared, m being the mass, c being the speed of light, but we have to be very careful here that that's in kilograms. The easiest way to do it is just to add 3 to the exponent. So that's actually 10 to the minus 24th grams. That would actually be 10 to the minus 27th kilograms, keeping in mind that there's 1,000 grams for every kilogram. And if we plug in that number and we go take my mass, keep in mind it must be in kilograms, and we're going to multiply that times speed of light, and we're going to go out 5 significant figures with the speed of light just to keep up with how many sig figs we're doing so far, and that's 2.9979 times 10 to the 8th, and of course that's meters per second, and we have to square that up, and we put that in there, we get 2.7827 times 10 to the minus 10th joules, and that's per atom. You can on your own if you want to decide, well, what if I was to do 92 grams? In other words, 1 mole of uranium, you'd have a bazillion joules of energy, which is why nuclear power plants and fission is so powerful. Okay, so there you have it. We have our mass defect and we have the joules if we start with grams. Now let's do a similar problem, except this time we're going to do it in what's called, yep, not that one. Let's go back to slide number 2. Here we go. Let's do this in AMUs. So we have an aluminum 27 nucleus, and it has so many AMUs, 26.9744071 AMUs. An atomic mass unit is the same number, approximately same number you see on a periodic table. Of course, the number you see on the periodic table is the weighted isotopic average, but it's pretty close. So that would be 26.97 grams per mole is what essentially this amounts to being for the nucleus. Now, once again, we have already taken off the electrons. If we had electrons on there, we'd have to take them off because they're not involved in the binding energy. So this is the nucleus without the electrons. So let's see what we get here. What's the mass defect and what's the binding energy? So we're going to do a similar calculation, except this time we're working in atomic mass units, but eventually we'll get to kilograms and then finally into joules. And so let's see what we have here. So the first thing we have to do is add up the protons and the neutrons. So we have 13 protons, and we're told that it's 1.00726765 AMUs. And we're going to add in the neutrons. Well, 13 from 27 gives me 14 neutrons. And once again, we'll go ahead and add those up and together. 6649 AMUs for the neutrons. And we add them up and we get 27.2159031 AMU. And this is our calculated mass that we'd get if we assume that the nucleus actually weighed the same as all the neutrons and atoms that are added up. And so now we have to subtract off the actual measured mass, which is 26. Here we go, 26.9744071 AMUs. And that gives us a mass defect in AMUs of 0.2414.960 AMUs. That's my mass defect. Now, we can't plug in AMUs for our binding energy, which is E equals mc squared, but what we can do is we can convert our AMUs into kilograms, and that's easy peasy. So we say a 0.2414.960 AMUs, and an AMU is 1 gram is 6.0221421 times 10 to the 23rd AMUs. This is Avogadro's number, by the way, times 10 to the 23rd. And that'll give us how many grams do we have in AMUs, but we need kilograms because in E equals mc squared, the mass has to be in kilograms. And so we'll say 1 kilogram is 1,000 grams. And now we're almost there. We put that in our calculator and we get 4.0101345 times 10 to the minus 28 kilograms. And then we're going to multiply that times the speed of light, which is 2.9979246 times 10 to the 8th meters per second. And we're going to square that up. And we get a final answer of, once we put this in our calculator, 3.6041 times 10 to the minus 11th joules. And there's our mass defect for an atom of and binding energy for an atom of aluminum 27. Now, I do want to point out a couple of things here. First off, your mass defect is going to be point something. 0.2, 0.3, 0.5. That's going to be your mass defect in AMUs. And your energy, your binding energy, is going to be somewhere around 10 to the minus 11 for all the atoms. Some are 10 to the minus 10th, 10 to the minus 11, but they're all in that ballpark. So keep in mind that's a pretty good check to decide whether you're where you should be as far as the calculation goes.